You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. Shelley Wright. Dr. Wright earned an astronomy PhD in 2008 at UCLA and is an observational and experimental astrophysicist that studies galaxies and supermassive black holes. She also specializes in building optical and infrared instruments for telescopes. As part of SETI, Dr. Wright is a researcher and instrumentalist leading the team at the University of California, San Diego Optical and Infrared Laboratory in building the instruments for PANOSETI. The Pulsed All-Sky Near-Infrared Optical SETI Observatory will be a dedicated SETI facility that aims to increase sky area searched, wavelengths covered, number of stellar systems observed, and duration of time monitored, offering SETI an all-observable sky set of instruments in the search for technosignatures.
Shelley Wright, welcome to the program.
Thank you. Thanks for having me today.
Now, you work in an interesting area of SETI, near infrared. What is the advantage of looking in that area of the electromagnetic spectrum?
I work in both optical or visible light and the near infrared, and they all have distinct advantages. Some about the transmitting scheme and some about how you may even receive a signal. But you asked about near infrared specifically. So similar to radio wavelengths that are easily transmitted and easily traversed through our Milky Way galaxy and doesn't get absorbed or reduced by the intervening gas and dust, the same is true at near infrared wavelengths. So wavelengths of light that are just longer than what we could see at the visible spectrum. And that light can also traverse through our Milky Way galaxy. And I like to think of that as like a Frisbee disk. And it's a Frisbee disk of stars and dust. And you need longer wavelengths of light to be able to penetrate that dust. And so one of the distinct advantages is that in the near infrared, you can use optical or visible light techniques, like optical telescopes, but you don't get this intervening absorption, or what we like to call extinction in astronomy.
With that would imply basically laser communications, right?
One of the most fond things to think about for today's technology, if you were to transmit a signal, and let's say you wanted to go tens or even hundreds of thousands of light years away, the laser is an incredibly powerful beacon that can be used. One, it's directional, meaning that if you launch that laser in a particular direction, anybody on the receiving end would be blasted. It would be incredibly bright. And in fact, if you take the largest lasers on today at Earth and use our largest optical telescopes, we can outshine our sun by factors of 1,000 and still have a little small telescope at the other side of the galaxy that could detect it. And so in optical SETI, which we like to think about the transmitting scheme, and lasers are fantastic ways to communicate across interstellar distances. But there may be other ways to communicate that we haven't invented or we just don't know yet that uses those similar frequencies.
This seems, wasn't it, correct me if I'm wrong, wasn't the idea of laser communications in SETI actually formulated originally by the guy that invented lasers?
Yes, Charles Townes, 2 years after he invented the laser, realized what he had invented. I mean, he was obviously a remarkable scientist, but he was a scientist that invented something and knew that it would be transformative across all of our industries, medical to telecom. And in 1961, he published a Nature paper that essentially said that using the laser would be the best means for interstellar communication. This paper was quite detailed. He even talked about different frequencies of the lasers. Given the things we just discussed about absorption of gas and dust that are in our galaxy, he even considered that. And he also, in that same paper, predicted that we would use lasers through communications through interplanetary satellites, meaning we would communicate from Earth to Mars using lasers. And this, in fact, is happening now. NASA's launching a new mission to begin doing basically interplanetary communication using lasers. And it's just remarkable to me that that just occurred only 2 years after he invented this. It's amazing.
It is. And now let me ask you this. Would communications be the only thing you would use it for? Could you use lasers, say you're an advanced civilization, for energy transfer, or are there other uses?
One of the ways they try to explore interstellar travel is what we call radiation pressure. So if you shine a lot of light, intense amount of light, potentially into, let's say, a solar sail, a very large sail, and if you transfer that light, the light will push on that sail and accelerate whatever the mass is attached to it. And so, in fact, there's things, like Breakthrough Starshot that's being explored to use lasers to essentially build spaceships and do interstellar travel. People have even thought, in bringing it back down to optical SETI, is that if people, or let's say aliens, were out there using interstellar sails with lasers, that perhaps there could be leakage from such travel and we could detect it as well.
Now, it's much, much more broader than communications. So by looking and using an instrument like PanoSETI, we could look also for accidental detections of aliens doing other things like laser sails and things like that. But what would the difference be? I mean, if you're looking using that instrument and you're looking at that and you see leakage from a sail versus an intentional communication, how do you differentiate between the two?
That's a very good question. It could be the location for which you detect it. So maybe you get a laser signal that's not near a star, but it's also in the field, potentially between stars. So it's implying that there's some ship that's outsourced it. It could be the timing of the laser, whether it's being it's actually just being continuously emitted, or if it's pulsed in a very unique way where we think it could be used for laser sails. So there's many different aspects that we could see within a laser launch. It's a difficult thing to assess. One of the things, a good thing about PanoSETI is that what we're trying to do is look, everywhere, all the sky, all the time, right? And previous SETI searches, both radio searches and optical searches, looked at one star at a time and asked if there's a signal. But if you're able to do large fields of the sky at a single moment, you can detect things that are potentially signals coming from around a star, or a signal that's not coming around a star. And that could be an interesting way to see if we would detect something we did not know. The other aspect that I don't think we've discussed yet is that at radio SETI, so when you look at radio signals, you have to scan in frequency. So I always like to think of this as you're in your car, you're driving, you want to find your favorite radio station, 93.1, and you're scanning to that exact frequency of light. At optical SETI, or even near-infrared SETI, we don't have to tune our detectors into frequency space or wavelength space. We can just say, is there a bright flash, or is there a lot of light that's coming across the entire bandpass? So, very all across the spectrum, across optical, ultraviolet, and near-infrared. And that's one of the distinct advantages of optical SETI compared to radio SETI, is that we can just look across many wavelengths at once.
But once you see a signal, just given its laser, it's probably going to be very narrow band, right?
It will be very narrow band. That's true. We would see a very intense light. And then the other aspect of it, it could be a pulse light that's occurring, at very fine time resolutions. Maybe it's episodic, maybe it's periodic. Okay, that would imply that it's artificial. And once we would have a signal, then of course what you would want to do is then look at that part of the sky with a spectrograph or a spectrometer and find out what frequency that laser signal would be coming at. And it should be very bright in the spectrum.
Now, give us an overview of the PanoSETI experiment. What is the ultimate aim? How are we going to look for this stuff?
So previously, for the last several decades, optical SETI had done what's called targeted searches. So they would build very fast photometers that would look at nanosecond regimes. So they would look at every nanosecond at a particular star and ask whether there was a bunch of photons that arrived at once that made it look artificial, or could be pulsed like a laser. There was one other experiment by Harvard that tried to do a wide field search where they just looked at a patch of the sky and then just scanned over that patch to see if there was any bright pulses. SETI is like a needle in a haystack, and the parameter space is incredibly vast. And so the challenge that we were trying to look at was, how do we look at the entire sky, the observable sky, and how do we do that all of the time? So we don't have to point our telescope to one, star at a time or one area at a time. And to do that, we needed to kind of merge several instrument technical techniques. And I'm really pleased with what our team came up with. Of course, if you want to look at many parts of the sky with an optical telescope, you need hundreds of telescopes, okay? And if you have hundreds of telescopes, that gets very expensive. And so we needed a very cost-effective way to do this. And what we're using are Fresnel lenses. And Fresnel lenses, people may hear of them, they're used in lighthouses, right? We beam light out into Fresnel lenses, which makes a nice beam. But Fresnel telescopes can be used for imaging. And so what we're using are basically half-meter size, so about 20 inches in size diameter lenses that are Fresnel lenses. And that focuses down, and each lens gets about 10 by 10 square degrees on the sky. And on the back plane, we use detectors that are able to read out every nanosecond. And so we have, for a given observatory, about 100 of these Fresnel lenses. It kind of looks like a fish eyeball or a fly's eye, so to speak. And the fly's eye is looking at the sky, and each little Fresnel lens images about 10 by 10 square degrees. And it's taking a picture of the entire sky every nanosecond. And we're asking if there's a laser pulse or a laser signal, or maybe something we haven't thought of, a burst of light at that time resolution.
Could you do other science with that? I mean, once the instrument is built, can you collect other data for other purposes?
Yeah, that's a great question, especially in the area of astronomy where we like to think about transients. There's things called fast radio bursts that occur at very fast timescales, and they're kind of mysterious sources. We're interested in potentially if there's optical counterparts for radio pulsars, which we had seen for like the Crab Nebula. There's now with LIGO, there's very interesting things to look for electromagnetic counterparts, or I should say the light or optical counterparts to neutron-neutron star mergers or black hole to neutron star mergers. And one of the nice things that we're doing with PanoSETI is on the back end, we can read out the observable sky every nanosecond, but we've designed our electronics to be able to adapt that to, every microsecond. And we have astrophysical interests to see if we could potentially, see counterparts to when there's a LIGO event or when there's a supernova event, because we'll be recording this information. And the answer is we don't know, because there's never been an instrument that just looks at the entire observable sky all the time at these time resolutions.
Yeah, especially at those time resolutions, it's nanoseconds. Now, let me ask you this. So if you see something that appears to be a laser emission from an alien civilization, can anything in nature mimic that? Or is it, this must be technological? Or is it, well, we don't know, we need to watch this, how unambiguous would it be?
That's a great question. And one of the leading, problems for any SETI experiment is how to make it unambiguous. So I described an observatory where we have hundreds of Fresnel lenses. What I didn't describe to you is that we want a second observatory. And that second observatory will exist about 1 kilometer apart. Okay, so we want them separated, and they'll be able to image the sky. And if one observatory gets a burst, it's very unlikely that the other observatory would see the same burst with that time delay, by the way. Okay, so about a nanosecond is about 1 foot, of travel distance. And we can look at the time delay and see if it arrived to both observatories. And that's how we will confirm if there is a pulse detection on sky and if it's real. Okay, but let's get to your other question. How do we know if it's aliens or if it's just nature? The answer is, if we just got one signal, we may not. Okay, and just like when we think about the wow signal, right? It only occurred once. Okay, so you just left scratching your heads for decades. Now, if it repeats, which it would need to if we wanted to follow up, if it repeats at maybe an artificial repetition, or maybe it repeats to something that is known in nature, and then maybe it repeats and it's on a point of the sky that does have, some known natural source that's a compact object. So there will be lots of, if any signal happens, whether it's optical or radio, we will have to follow it up with other means. And it has to be repetitive. Otherwise, I don't know how I can come on a show and say we got a detection and it's been 100% proved.
Now, speaking of the WOW signal, within optical and near infrared, do you have WOW signals? I mean, have there been candidates that detected by you or any other team that seemed to make you scratch your head but didn't repeat?
We've had signals that has made her scratched her head for a few weeks. So we have candidate levels where it's occurred. So we built another instrument called near infrared SETI, NIRO-SETI, which was the first near infrared SETI search. And that was a targeted search where we look at one star at a time. It's still running. And in that survey and in other previous optical SETI surveys, we've had, potential blips. And we've had to go back and look at what caused it. And in most, if not all cases, we've attribute it to an instrument noise within our system, or predicted that we'd have some false alarm rate within it. But nothing that we could not later explain. But there's been a few exciting days or weeks where we've had to follow up. But we've had nothing that ever repeated. But
the day is probably coming where it won't be a false alarm. How common do you think alien life in the Milky Way is? That would be detectable. Just in your own, telling yourself a story. How common do you think they are? Do you think it's very rare, or do you think the galaxy teems with civilizations?
Well, there's two questions in there, right? I think that now that we understand that Earths aren't rare and exoplanets are everywhere, I think life is common. I do think that there are other civilizations coexisting with us now in the Milky Way. But to get to your SETI question, how common are they communicating? I just don't know. I mean, of course, none of us know. But I suspect that if we were to guess the exact way that they were transmitting, that would be incredibly lucky. So part of SETI is that it's a vast, if you look at the electromagnetic spectrum, or light as we like to call it, we have gamma rays and X-rays and microwaves. We have near infrared wavelengths, radio wavelengths. The space is so vast that we are still just chiseling away at it. So it's a great question. We don't have an answer, but we're searching. So, but you're asking my what I think. I think there's likely other civilizations out there leaking or potentially communicating, but I don't think it's that many.
Now, say we have an intentional, somebody looks and sees Earth and they see this weird, exoplanet with, strange oxygen levels and everything else that's obviously being influenced by life. So they say, okay, we're going to send a laser signal towards that planet just in case somebody's there. And they do that. Do we ever have any hope of decoding it? If there's a message contained in that optical signal, do we have any hope of decoding it, or would we just simply say they're pointing a laser at us?
So the answer to that, I think, is if they were transmitting and they were using a laser and we could identify that narrowband laser, I think the answer is yes. I don't know how quickly. And the reason why is because we've gotten so good at telecommunications now. We're constantly using lasers going back and forth between our satellites now. And what we do is we modulate that laser, and you can pack a ton of information into a laser. That's another advantage of it, right? The fact that we're in 2020 and humans could take our present day technology and encode the entire internet on it and launch it and have it received by a small aperture 10,000 light years away is incredibly remarkable to me. Please don't anybody do this. I don't think we need to pack the entire internet into a laser signal. But the point is we can do that now. So if you look at transmitting schemes, we could. Now, I think we could try to decode a message. Will we know what they're saying or what TV show they sent us? That will probably take decades for decoding. We'll need anthropologists to figure this out. So the technique for modulating a laser and receiving it, I think we could try to do. What it actually means and the content, if we could understand their version of Shakespeare, that is up for debate.
Just the idea, though, that, say alien scientists sit down and decide, okay, we're going to send out our entire scientific knowledge what we have learned to everyone else, and just the potential payoff of detecting a signal like that, the Encyclopedia Galactica, is astounding, because then you might have things like images, direct images of their planet or them, things like that. And while it might take you 1,000 years to decode it, it still would be the biggest game changer a species could have, I would think, in this universe, right?
That's right. It's almost like imagining going to ancient Egypt and dropping them a motor car and a television, right? You have no idea what level of technology that would be arriving at our doorsteps in a sliver of time. And of course, this brings up a lot of debates about SETI. And, a lot of the questions come to it is, if we ever do get a signal, how do we make it where it's accessible to the entire world, meaning that information, because it could be incredibly powerful information.
Now, to get back to PanoSETI, this seems to me to be really economical as well, through the use of the Fresnel lenses instead of other telescopes. So what's it going to take to get the entire project realized?
So we've spent the last 2 years building all of our prototypes. So we have several of these telescopes. We have a couple of them operational now at Lick Observatory. In fact, we're observing this week using the telescopes. We've spent 2 years designing all of our back-end electronics, how we actually take the data at nanoseconds, record it, analyze it, all of this in real time, how we can adjust in timing. So at this point, PanoSETI, we've retired most of all the risks for doing the project. We are now in the design phases. So we have an observatory designs of how we want to house all of these hundreds of telescopes in geodesic domes. We're in site selection. And so we're prepared to move to the next phase where we actually break down, at the end of this year, or the summer, we were supposed to break ground. That's been delayed because of COVID-19. But we're looking to build this thing in the next year. And I'm incredibly excited, and the entire team is excited. So this is, where we're at, that we're trying to put this kind of idea into realization. It will be the first kind of dedicated SETI observatory at optical wavelengths ever. And it will certainly be one of the first observatories where we try to do very fast time resolutions over wide fields of area on the sky. Every time astronomy looks at a new regime, we often discover something new about nature. And that's probably where a lot of my excitement draws from.
Well, that's going to be interesting too, in and of itself, is the stuff that you don't expect, because at that sampling rate, think about like with the Vera Rubin telescope, where you can do optical sky survey every day and a half, and you can do it on nanoseconds.
We can do it on nanoseconds. We're not nearly as sensitive as Vera Rubin, right? So we're looking for incredibly bright, like the really bright stuff that occurs in our universe, but occurs very, very briefly. There's no nice way. How do you say nanoseconds? Incredibly, very, 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 it's very brief. So it's very unique.
And incredibly exciting. I'm particularly interested in this particular project, because anything all sky is fascinating to me, because that's where you see the universe in real time, essentially. And you can see how it changes on a second-to-second basis, as opposed to a century-to-century basis, or millions of years basis, which is how we sort of saw it, in the pre-telescope age, where the unchanging sky, even though it's changing. But then when you look really, really carefully, it's changing all the time. And that excites me about current instruments that are coming online, is because they can see that. It's like having a video camera on the sky instead of a still camera.
It is a video. I was just smiling to myself, because in our recent observations on sky, we can see satellites and planes, and we have a very active atmosphere. So we're observing it on very fast time scales.
Now, can you actually see? Now that's another question. Is that, can you tell meteorological data and stuff like that from it? Could other scientists in other fields use this idea to study the atmosphere, say?
What we do detect, so most of our noise actually has to do with Cherenkov radiation. So when cosmic rays hit the top of our atmosphere, it generates a showers of high energy particles that come showering down. And that's actually our noise. But because we have 2 observatories and we use multiple telescopes, we can easily see when that shower occurs. And so the other science area we haven't talked about has to do with cosmic rays and what's called Cherenkov radiation. And we will observe those events and record them. And so that's the other scientific area for this.
Now, Cherenkov radiation, that's also the same stuff that you see coming off nuclear reactors, isn't it?
Yes, yeah.
Now, You also have involvement from other SETI, prominent people within SETI, Paul Horowitz and Frank Drake, I see. How did they get involved?
Well, Paul Horowitz was actually one of the early optical SETI pioneers. Of course, he was an early radio SETI pioneer. Very soon after Frank Drake came on the scene and did his Project Asthma, many years later, Paul came along and did radio SETI. And then he was really struck by Charles Towne's paper. And then it took until the early 90s when the first optical SETI projects kind of sprung up. And Paul was one of the first ones. The other one was Dan Wertheimer at Berkeley that also began to do optical SETI. And Paul is the only one who's actually done a little bit of a wide field optical SETI instrument before. And he made a little dedicated telescope at Harvard and Princeton. Frank Drake has always been interested in new SETI, regimes and expanding the search for SETI at different wavelengths of light. And in fact, I first met Frank Drake when I was an undergraduate. He was my undergraduate mentor, and he was the one who wanted to kind of move into optical SETI at that time. And so we worked together with people at Berkeley to build, some of the first optical SETI detectors about 20 years ago.
Now, if you had to guess, once you get the full array up and going, do you think it's likely that we will see something, say, within a 20-year term? I know Seth Shostak always predicts that within 20 years we'll probably see something. Do you think that's realistic, or do you think that this could take much longer, or almost could it be almost immediate, a detection of a really strong candidate?
I suspect when we first get on Sky, we are going to have some strong candidates. I think we're going to basically get on Sky and, realize that some of those candidates are just us fine-tuning our instruments. But I suspect we might discover something pretty quickly about nature, potentially, especially when we couple this to other wide field surveys that are happening and looking at counterparts. But if your question is about whether we get detection from, what we're really going after, which is looking for an alien civilization, I don't think so. I think we're really still early in the game. This is probably one of the things I've learned the most doing SETI research, is how little we have searched. I think PanoSETI is a fantastic step. It's actually orders of magnitude of leap, by factors of thousands of areas searched on Sky, factors of the millions of the number of stars searched at these wavelengths. But it's just one area that we're, trying to expand into. And so it would be wonderful if we got this right. But I suspect we're going to have to keep looking at new methods and techniques to explore SETI. And we need more people to do this and more outside the box thinking. Hope so is the answer, but I don't think so.
I think that's one of the misconceptions about SETI, is that the reality is we've barely looked. And it is a lot harder to search for, a technosignature like this than what was thought decades before. I think it was Cocconi and Morrison that started the whole thing, thinking about giant omnidirectional beacons and things like that. But those don't make any practical sense. So it's a lot more nuanced than I think anybody realized. And that's the real takeaway from SETI, I think, over the last 30 years, is that we realized that it's hard. Do you agree with that?
I think it is hard. I do agree with you that one of the biggest misconceptions from the public is that what scientists have been exploring at great lengths on this topic, and the answer is no. It's always shocking to me to know that, it's a mere couple dozen of people worldwide that do SETI. And we've mostly been doing this on a shoestring budget. So the level of resources dedicated to it are very, very minor compared to other big science questions that we have, where we throw millions and billions of dollars at it. So I totally agree. And that's why I think we need way more people. A lot of smart people need to come into it. And one of the things I love about SETI is it makes us think creatively about the universe. It makes us think creatively about technology and how to use it. We use a lot of similar methods for radio SETI and optical SETI from astronomy, but we have to tweak our instruments and our telescopes slightly differently to try to weed out a signal. It's actually different. And I think that difference is good. I think we need that as scientists.
I think another big misconception, too, is that people think that SETI is being funded by taxpayer dollars. And I always get that question. And Like, not in decades. This is all privately funded stuff and not subject to anything from the government.
Yes, and I always state that scientists are people and they need to pay rent and they need security in their career. And you're not going to go into a field where there's no funding level, right? Most scientists go into exploring health or neuroscience or bio, DNA research, right? Where there's public dollars coming in and there's money where you can sustain a career and answer those questions. But in SETI, you're living paycheck by paycheck. And so it's a hard career to get young scientists to engage in, which is what the problem is. We need to build up a workforce for it. So that is one of the leading problems of this.
What about crowdfunding? I mean, can you do projects like that and maybe get funding that way?
I think that's a great idea. It's good for like prototypes, I think. We've used that in the past where we may have a new idea and we want a small project to test out a new technique. But when you need to make large observatories, you want to make it sensitive. You're trying to detect a weak signal out in the universe. You usually need large apertures. You need really sensitive detectors, and it becomes pricey.
But not for bright pulses. So
bright pulses are not. Yeah, sorry. Go ahead.
Yeah. What is the? Do you have a protocol in place for a detection? If you see something with the instrument, what is the next step? Say you verify it, assuming you would go and verify. Do you just go public?
We have automatic software and we look at it by eye. So we have different levels of like candidate alarms that come in that we have to weed out very quickly. So we do a protocol internally within our team to, first decipher if we think it's a viable candidate. If it is, it essentially goes out to an astronomer's telegram and it becomes publicly known with the coordinates and the location on the sky. And so the astronomer's telegram is used for transient events like supernova. And so it would immediately go public because the most important thing you can do in that situation is get every piece of telescope and glass and dishes pointing to that area of the sky. And so that is essentially our protocol.
Now, it's worth noting that the astronomer's telegram is open to all. So you can go look at this and you will see the post in real time if you monitor the telegram. So there's no secrecy at all here.
It is public, and I get that question a lot. So it would happen very quickly. We purposely would not hide that information. It would go to the entire world.
And people like me would see it and talk about it. All right, Doctor, this was a great interview, and I wish you great luck with PanoSETI. It's really fascinating, and I think you're probably on the top of the heap as far as detection, where it seems likely to come from. If we do actually detect something, it seems like it's going to come from PanoSETI. So I wish you great luck in your project.
Thank you. I enjoyed being here, and our team is having great fun doing this project.
John, why is there acoustic foam everywhere?
I'm building my new studio.
John, why is the opossum the one putting it up?
He's good at it.
John, why is the opossum gluing foam to you?
Wait, what?
He's good at that too.
For God's sake, I'm sick. So sick.